You know that thing you do every single day, probably without even thinking about it, pinching and zooming on your phone screen? Well, it turns out there's some really cool geometry hiding behind that simple gesture. And today, we're going to pull back the curtain on it. So, have you ever actually stopped to think about what's happening when you resize a photo? It's not just some random clever bit of code. Nope. It's a really precise geometric transformation, and it has its own set of rules. And that transformation, it has a name. We're about to dive into the secret behind perfect scaling, which in the world of geometry is called a dilation. So, what in the world is a dilation? Well, put simply, it's a transformation that changes the size of a figure, but doesn't mess with its shape. It keeps all the proportions perfect. Think of it exactly like the resize tool in your favorite photo editor, just, with a mathematical brain. Every single dilation needs two key ingredients to work. It's like a recipe. First, you've got to have a center of dilation. You can see it right here as point C. That's our fixed anchor point. And second, you need a scale factor. That's the magic number that tells the shape exactly how much to grow or shrink. Let's zero in on that first ingredient. The center of dilation is the one point in this whole operation that does not move. It's totally stationary. Everything else either stretches away from it or shrinks right towards it. It's the reference point for everything. And here is our second crucial ingredient, the scale factor, which we usually just call K. This is the control knob for the whole thing. It's a super simple ratio. You just take the length of a side on the new resized image and divide it by the length of the same side on the original. That one little number controls the entire outcome. Okay, so we have our two ingredients, that anchor point and our magic number, the scale factor. So how do they actually work together? Well, it all comes down to some really simple rules of scale. The value of K tells you everything you need to know. If your scale factor K is a number bigger than 1, your shape gets bigger. We call that an enlargement. But if K is between 0 and 1, like a fraction or a decimal, the shape gets smaller, and that's a reduction. See? It's that easy. And this slide shows it perfectly. Look over on the left. The scale factor is 3/2, which is 1.5. Since that's bigger than 1, the safety pin gets enlarged. Now look at the right. The factor is 3/5, or 0.6. That's less than 1, so the paperclip shrinks down. It just works. All right, this is all great in theory, but let's make it real. Let's see how this actually works by putting a dilation into action on a good old coordinate plane. You're gonna love this. The rule for plotting a dilation is so simple, it almost feels like cheating. To find the new spot for any point, x, y, you just multiply. Your new point is just k, x, k, y. That's it. So, if you want to resize an entire shape, it's literally just a 3-step process. Step 1, find the coordinates for every corner of your shape. Step 2, multiply every single one of those numbers, the x's and the y's, by your scale factor k. And step 3, just plot your new points and connect the dots. Boom, you're done. Let's walk through one together. We've got triangle ABC, and we're told our scale factor is 2. So just look at point A. It's at 2, 1. We multiply both numbers by 2, and our new point, A prime, lands right at 4, 2. You do the exact same thing for points B and C, and there you have it, a perfectly enlarged triangle. Okay, so you've pretty much mastered enlargements and reductions. But geometry always has a cool little twist up its sleeve. What do you think happens when we push that scale factor into some, let's say, uncharted territory? So far, K has always been a positive number, but what if it's negative? I mean, what does that even do? Does the shape just vanish? Does it turn inside out? What do you think? And here's the big reveal. A negative scale factor is a 2-for-1 deal. It still resizes the figure just like before, but it also rotates the entire thing 180 degrees around that center point. It's a resize and a full-on flip all in one move. How cool is that? And of course, the math totally backs this up. The rule is almost identical. You just carry that negative sign along for the ride. Your original point x, y transforms into negative kx, negative ky, which sends it to the complete opposite side of the graph. Okay, so right about now, you might be thinking, this is a pretty neat math trick, but do I actually ever use this? Well, let's connect this all back to the real world and see exactly why this matters. Take a look at this. A magnifying glass is a perfect, everyday example of a dilation. So in this case, the image of the spider we see is 6 times its actual size. In geometry terms, what's our scale factor, k? Yep, it's 6. So if the real spider is 1.5 centimeters long, how long do you think the image is?
You just multiply. It's that simple. 1.5 centimeters times our scale factor of 6, and that gives us an image that's 9 centimeters long. See? A real-world dilation right there in front of you.
So the next time you zoom in on a map on your phone, or see the image from a movie projector, or even just watch your shadow stretch out on the sidewalk, you'll know the rules that are at play. It's all just dilations. So I'll leave you with this. Now that you know what to look for, where else do you see this perfect mathematical scaling happening in the world around you?